All right, awesome. Yeah, okay. So we'll be covering two papers today. I'll be going first. So lately, a lot of the focus has been on um, just measurement of all of these systems. So we're going so rapidly, everything's getting smarter, everything's getting faster, longer context length, all of these things. So this paper is from a group that their whole focus is just measurement and evaluation of all of these systems. Um, so the focus of this is basically they looked at it and they said, since 2019, we've gotten so much better. Like you look at something and it was like we used to be 0% accuracy, now we're 99% accuracy. But they wanted to look at real world tasks and understand like how much actual like real world utility have we grown. Um, and so what they did is they kind of retroactively looked at all of the past models and the history and then said, how quickly are we moving and what's our kind of rate of progress right now and what can we extrapolate given our current rate. Um, so they set up this benchmark and the whole focus was just find real world tasks. They're all focused on software stuff because that's what they know and what's easy to kind of test and quantify. And so they got four different benchmarks and they kind of merged them together. And then what they did is they said, have humans go try to complete this and time them and say, um, how long does it take for you to complete this and what is your level of accuracy? So can a human do this reliably? How long does it take for them to do it? And there's several different benchmarks that they've kind of squeezed together. So there's this HCAS set that has 97 different software tasks. Some of them are easy enough that you can solve them in a minute. Some of them are so complicated that it takes 30 hours to solve. And so this is kind of the thing that they're focusing on is like, how much better are we doing at longer and longer tasks? So you look at the very simple systems initially, and they might be able to guess the next few words reliably, but they couldn't write you a whole function or something like that. And so this is essentially what it's testing for is how long of a horizon can you actually reliably do a task? Um, so the RE bench one that they introduced, it was only 7 tasks, but they take 8 hours long for a skilled engineer. So it was stuff like optimize a CUDA kernel for some specific thing, where it's like you have to be highly skilled and you have to know what you're doing, and it still takes you a long time in order to complete it. Um, and then there's the other end of the spectrum, this software atomic actions, where it's little tiny bite-sized pieces, and we'll look at some of these tasks in a second, but it's like people who are skilled can kind of glance at this and just say that's the answer. It's not something that you have to like deeply think about. Um, so ultimately what they did is they benchmarked a bunch of humans and then they benchmarked a bunch of models and then they have this big pile of data and they say, what's the trend that we can see from this? So here's a few examples of some of these problems. So like the first one is saying find the shell script. So it's you have this list of files, which one is the shell script? So they can look at it and they can say, okay, the run.sh is the shell script. This is a text file, this is Python, this is Markdown, for example. But then the more complex ones, it could be all the way up to like do some CUDA optimization thing. You need to make something 30 times faster. And so very involved, much more difficult for even a human to do. Takes hours and debugging and lots of trial and error. And so would be very hard for um so here's the kind of this is the big outcome of the study. This is everyone's been showing this graphic and being saying like, wow, look at this extrapolation. And so what they're saying is back in 2019, we had GPT-2 and it could complete a task that was maybe 2 seconds long. So it was you just write the next few words or something like that. And then you get all the way to GPT-4 and you say it can complete this task with the one of the caveats to this is with 50% success rate. So it can do a 4-minute task 50% of the time. So that's kind of the complexity that they're measuring. And then the all the way over here looking at Claude, one of the latest models. we can see it goes all the way up to 1 hour. So 50% chance of completing a 1 hour long task is fairly advanced. And I think the scale of this doesn't really show like how massive that gap is. Like this is 2 seconds, this is 1 hour. That means we've doubled the ability to do longer and longer tasks multiple times. So one of the things that they were keying in on is the doubling time. So they're saying we've doubled the length of task that we can complete with 50% accuracy every 7 months. So in another 7 months, in 14 months, we'll have maybe 4 hours, 2 hours, something in that range. Yeah.
Just a quick side comment. Um, you know, people talk about intelligence, they talk about different things, and there's often a lot of debate, but it's really hard to measure intelligence, right? And so what I love the fact that this is something that's, I think, pretty accurate. If you test like 100 subject matter experts, right? And on average, it takes them 30 minutes to do this.
Yeah.
Then like you have a pretty good judge of that task, right? So that's the thing I think is a huge takeaway from this is that this seems way better calibrated than any other measure of, MMLU or, GSM-8K,
Yeah.
that kind of stuff. So
Yeah.
I think really kudos to them
Yeah.
for coming up with a way more accurate way to calibrate it.
Yeah.
And actually, one thing I'm kind of curious about, a lot of this seems around software engineering, and that does seem to be the interest community of ours, that most people here are some sort of software engineer, but I also see it mentions general reasoning tasks, and I'm wondering what the extent of that is. Like what kind of, like are we solving logic puzzles in abstract? Are we, like what kind of general purpose tasks are being done?
In this, it's all focused on the software engineering. So the general reasoning that they're including there is like its ability to think through the problem and understand, oh, I need this bit and that bit in order to update the code here.
Okay.
That's yeah. So it's limited to that. It's not necessarily advanced thinking problems or something. I saw people on Twitter actually talking about how like we've really gone up the stack in terms of math and programming, but the models are still actually fairly weak at like physics and other kind of domains. And it's kind of just we figured out to make data sets and optimizations for those things. And so like reasoning and other things we're getting better at, but the whole focus is basically just coding.
I'm optimistic, but once you unlock this idea, you could have people time what takes people 5 minutes to do an Excel, what takes people half an hour to do an Excel, it takes only 3 seconds, right? And you could have somebody, I don't know, book a travel itinerary, and then again, you could just like, I feel like it's a really
Yeah, it does feel like the right approach compared against the human.
Yeah, and compared to just everything else, where it's just like this was a hard task.
And
I actually have a quick question about that. So did the paper mention anything about like, I see that that's like a linear relationship right now, but do they mention anything about like a task that like takes say like an hour? Is that like do we consider that exponentially more complicated than a task that takes 30 minutes or like linearly more complicated? I'm kind of curious, like
that is an exponential scale though, isn't it? You're doubling your time, yeah.
So y-axis is the lowest scale.
oh, it is actually.
Yeah.
Oh, okay.
Yeah.
So
yeah, that
But this is on time. They didn't necessarily do something to quantify the gap in complexity. They talked a little bit about messiness that I'll talk about in a second, but this is an exponential scale. So it's saying like that's what I was mentioning earlier. Like the difference between 2 seconds and 4 hours is not really. Yeah.
Oh, it says 50% rate. So is that threshold at which the success rate must be in order to assess the time period of success of completion of that?
So they tested it on these 169 tasks, and they set a threshold for you need to complete at least half of those tasks, basically, at that threshold of time. So it's saying you have to complete at least half of the 1 hour tasks or something like that.
Out of curiosity, did they do it in the same order, or is there any possibility that the machine learning is saying, hey, these are the ones that are quickest to solve, we do those first?
They're all independently timed, so the ordering doesn't necessarily matter. Yeah. Um, so this is an alternate view of the same thing. So it was already saying Claude 3.7 was the best, but this is just measuring the success rate, just the pure success rate across all of our tasks. So we see Claude 3.7 Sonnet is able to complete 60% of the tasks overall out of their sets from the various different batches. And so O1 does a little bit worse, and you can see GPT-2 completes maybe 10% of tasks, and that's probably all of the very simple 2-second ones where it's just saying find the file or something like that. So then the next thing that they were plotting is the relationship between the human completion time and the model success rate. So this is basically saying for all the models, just what's the rate of completion versus the amount of time. So you can see for these like 16-hour tasks, none of them are able to complete that yet. But for 8 hours, you have maybe it gets a couple problems right, and lower and lower. And you see at this point, it's like, okay, all of the models can complete a 1% task almost all of the time. So one of the things that they mentioned is there's still a little bit of noise within this. They don't think that they can really measure like 100% success rate on any of these things because some of the tasks are just broken or messed up in some way. So they set that 50% threshold as kind of like, we know this data is a little bit messy. We don't expect 100% out of anything, but they said 50% seems to be a good threshold to aim for. Yeah.
This this kind of reminds me of how I use agentic systems, right? Because what I do with agentic systems, I just create a more like a more partition form of creating a task, you know. And so for me, this actually like just really contributes to my notion of how powerful agentic systems are breaking down tasks, able to delegate particular simple the things that would have taken more time into smaller pieces, right? So to me, this basically is a testament to the power of agentic systems when you actually have to break down tasks that may be an hour to complete into several months in order to complete it.
Yeah. I think one of the big things here is showing that that threshold is actually changing. So initially we had these models where you can only use them for these tiny little things, and that slowly shifted to you can have them write you a function, you can have them write you a whole file, you can have them go do research for you. Like we're pushing that further and further. So it used to be you give them a tiny little task and then they can do it, and it's extending further and further what can be done. So it's still useful. Like if you can say break it into smaller chunks and then I get higher reliability of each of those individual pieces. But I think we're getting to the point where it's like we can give more fuzziness and longer work sessions and just give a basic prompt and then say go figure out all of the steps instead of needing to say do all of the little bits and pieces and prompting yourself.
I feel like, Mom, if this is a good way to measure capability, then you might be able to show that my agentic system based on Claude code is actually further on that chart, right? Like I can now get 2-hour tasks done half the time, whereas vanilla Claude code can only do 1-hour tasks half the time.
Yeah.
I think all the buzz around agentic systems, there are many people who believe that is the case, but I don't know that we've had a great benchmark. Like that bar chart, I feel like we've had a lot of those bar charts. Yeah. And it's like kind of vague, like, oh yeah.
What does 60% mean? Yeah.
What does that mean?
Yeah.
So it's like the transition from that bar charts to that time chart.
Yeah. I think looking back at this one, like most people look at it and they go, it's right 60% of the time. I don't want a system that's right 60% of the time. But when you look at the spectrum and you say, oh, I have something that can do 99% of the time past a minute or something like that. There's lots of 1 minute tasks that you can pawn off to the system and say, do this, and you will most often get the right answer.
Still have to be the system engineer, know what blocks connect to what, and then once you just throw the blocks to algorithm will just do it for you.
Yeah.
I'm sorry, you've been very patient.
I didn't miss it, but what was it's human time to wait for subject domain experts? Was that the
It's an experience program.
first experience programs?
Yeah.
So
So if the programmer takes 4 hours, only one of these programmers was able to complete with a 50% success rate.
okay, what is the so like why is that? Why is human
It's basically say, hey, humans can do this in 1 minute, our AI can do this 90% of the time. And if it takes, if you want 4 hours, this AI can only do it half the time. It's not measuring the amount of time that the AI takes, it's just given enough time, is the AI capable of doing it at all without moving tool?
what about the I mean in some ways it can also be just
I think
what is
the
what
core
what
idea
metric
is that they
how long-
divided up the tasks into how long it takes a person to do this.
Yes, but I mean,
So
is it considering like what is problem solved for that? Because like if you're given like 1,000 long division problems, it can be like 4 hours to do it, but would take the machine fraction of a second. So my question is, I guess, like what level of abstract thought is required to
They made up a bunch of tasks, they measured the time it's people to do it. And then they categorize those tasks and say, oh, this is a 4-hour problem, this is an 8-hour problem, for the people to do it. And then they're not measuring the time that the AI takes for it, they're just saying, can the AI get it correct?
So Ryan, you should probably answer this, but I believe these are all single tasks. So it's not like it takes you 4 hours to plant 100 trees. It's like, how long does it take you to do one coding task? Like that hard one was make this CUDA kernel 30 times faster. Like nobody can do that in 5 minutes, right? And so essentially the key idea is they use how long it takes, and I don't know what the sample size is, but again, even if you nitpick at this, you could always use the technique and scale it up and say, now we tested on 100 programs, 1,000 programs, or whatever, you know what I mean? Like clean up the exact details. But basically we said, we rank the problems based on how long it takes a person to do them, not some abstract concept of complexity, right? So we don't actually know how much more complex an hour task is than a 10-minute task. It might be 10% harder on some measure. It might be 500 times harder on some measure. All we're saying is though, this human took 60 minutes and an average skilled programmer, 60 minutes, this average skilled programmer, 10 minutes. And if you then plot this, it turns out that it's not like a random thing. It's like actually a very, 2 plots of how many models get it right, and then the progression over time as we think of models that are getting bigger and more capable, what did the results actually look like, and they could fit it really well.
Even labor time is a baseline for sure.
Right. Right. So because of that, because they're not yet trying to equate human labor time to true complexity, if you then said like, I don't know, planning the days, the months work for, salespeople traveling around the country or whatever, right? Nobody knows how complex that is, and so we don't actually know how long it might take an agent to. But if you can say like, this would take a person 8 hours, then we kind of have a notion of, oh, if that level of complexity, then models aren't there then. That, oh,
a little bit. I have issues with it, but just it's okay. I understand them.
Just to add color to this. So here's some of the example tasks. So it's like one of these is saying you have 2 files. One of them been converted to a new format. Write a Python script that converts from this format to that format. And so that's an example of one of those tasks where a human took 56 minutes. Can the model, can the agent, can whatever do it at all? That's kind of the question that we're getting at. Yeah, go ahead.
Just to throw two more data points on the previous graph. I think I mentioned my simplified constrained Rubik's Cube question that I had asked the various LLMs. DeepSeek is the first one. It's 70 billion parameters that could do it. A lot of the others all failed entirely, no matter how much I tortured the problem. Quen 3, which just came out, the 32B one could do it. It had a color wrong for one of them, but it was otherwise correct. And the 30, which has a mixture of experts 3, which runs out lesser parameters, was able to almost do it, but then lost all color and was all collapsed into a weird two-dimensional shape.
Interesting.
And that's like those 4 or 5 days.
So here's some more charts, and I have GPT-2 in its little box of shame. So here's all of the latest models. That's kind of small, but it kind of matches with the stuff that we've seen on previous slides. So Claude 3.7 Sonnet, it has 50% accuracy all the way out to almost an hour, so 59 minutes. It can complete tasks almost an hour long, 50% of the time, which is getting quite long. That's impressive that it can do that. And if you compare that even to Claude 3.5 Sonnet, the previous one, it can only do 28 minutes. So that's a doubling just from 3.5 to 3.7. And then you can see from the old Sonnet, 18 minutes, Opus, their older one, and O1 does 39 minutes. So all of these are getting up into the minutes, maybe almost crossing an hour. And then you look back at GPT-2 that came back in 2019, and it can only complete 2-second tasks up to 50%. So it can't even I remember interacting with that model back in the day, and it was like, okay, it can write me a little novel and maybe its grammar is correct. And that was impressive at the time. But now it's like we have so much more than that. And it's just been continual scaling up of more data, more compute, more parameters, better post training, all of that stuff. So we've come a long way in 5-6 years, however long it's been. So then one of the other things that they looked at was how does things change if we focus more on the reliability? So before we were saying 50% is our cutoff. Does our trajectory change if we go up to 80%? That's the big thing, because we say, okay, we need reliability to be higher than 50%. Let's say 80% is our new threshold. And then they found that basically the trend still holds. All of the better models are still better at that success rate. And it shortens the time span. So before we saw like probably 59 minutes at about an hour, and we see Claude 3.7 is now more at like 15 minutes. So it can do 15-minute tasks 80% of the time. But one of the things that they noticed was that the doubling rate still is on track. It doesn't really change things. So even at higher success rates, we see that it's still continuing to get better at similar rates. So if you said 50%, we go double in a certain amount of time, 80%, we're also going to double in that same amount of time.
What's the button like? The rate loss?
That's the 50% rate, I believe. Yeah. Yeah. So you can see it's just shifted down. So all of the models are shifted down. The 50% rate is one doubling higher basically, but it's roughly the same.
That's great news.
Yeah.
You can imagine the 50% success rate would keep growing, but that the hard problem is might not grow as fast. Capability. But it seems close to parallel.
Yeah.
But wait, it seems that basically by increasing the 80% success rate, we're decreasing the task time that it takes for the model to complete it.
Decreasing the capability that it can only complete shorter tasks.
Oh, that's
Yeah.
what it is.
A lot of times
Gotcha.
you get the rating.
Yeah. So one of the things that they dug into was basically saying what is causing these systems to fail, and they went through and they categorized and they said of these models, what is their like reason that they didn't pass the task. So they said some of them are from poor planning. So it laid out a plan and it said, I'm going to go do this thing. And it was like that was never going to complete the task. If you perfectly executed on your plan, you're still not going to get to the final answer. Another section of it was incorrect mental math or reasoning. So it tried to add two numbers and it did it wrong, or it said, I think I need to do this and then that, and they had to do it in the opposite order or something like that. Another big one was premature task abandonment. So it says, I did this step, I did that step, and then it's like, okay, I'm done. And it just popped out an answer, but it didn't actually complete all the way to the end and get exactly what it wanted. So it just kind of quits early and says, I got it when it really didn't. And then the other one is repeating failed actions. So that was a common thing with a lot of the older, weaker models was basically it tries to run some code, it gets some error message back, and then it tries the same thing again, and then it fails, and then it just goes in that loop and it doesn't break out. I think that's one of the biggest innovations I've seen from Claude was when I played with it for Gaia and the various other benchmarks, it's like it's just impressive that it's so persistent and able to kind of break out of those loops. So it tries one thing, oh, the file's not there. Okay, I'll look somewhere else. And it just keeps kind of exploring and doing new things instead of the old models would just bash their head against the wall until they ran out of context and died. So that's one of the big things is I've seen that the repeating failed actions has gone way down, and we see that with the GPT-4 to o1. That's one of the biggest drivers. Another thing that they measured was the messiness. So they had 16 different characteristics, and they said if it matches this criteria, then you get +1 point per messiness. So here's just a few examples of them. So if it involved a novel situation, if it was constrained by a finite resource, if it involved real-time coordination, if it was sourced from real world context. So each of these gives a point to messiness. And so messier tasks are probably harder for the model to complete. If you give something that's very well defined and very straightforward, then it's probably going to be able to complete it. So their example was like, if you just tell it, write a good research paper, that's very vague. It has to go understand what are the requirements for that. There's a lot of things that are undefined there. So they're saying that would be between a 9 out of 16 and a 15 out of 16 for messiness. So it reaches a lot of their criteria for like, this is not well defined, it's very messy. It's probably difficult for the model to actually do this.
That's
Yeah.
a question. I'm not totally understanding why it's constrained by a finite resource contributing to this.
I think I don't entirely know what they mean by that, but one of the things that they were talking about was there's certain things where it's like you only get one try at this or three tries at it, and then you get locked out, or you mess with the database too much, or uh, you don't have infinite, like you can't just try, and then eventually get past it. That was my interpretation of it. At least.
That also be the data maybe that it is restricted to some data set and can't explore outside.
Yeah, yeah. I don't know exactly what the constraint is. Yeah.
My thought is more on that point, because with the Rubik's Cube thing, I say don't use the framework that you would normally use to solve that type of problem. So there's less data that you can use as a comparison to just copy off of.
Yeah.
That's why, like, you could try that and say, don't use a plugin to render Flash. Okay, that's a much harder problem than to, hey, here's an old Flash video play from.
Yeah.
Yeah,
Maybe,
that's what I was thinking. It's like, if there's a programming problem and there's this really easy way you can do it in n squared memory, and then you constrain it and you say, no, you can't use more than n log n memory. There are ways, but then like you can't just go to the textbook and really just say, well, here's this really easy thing.
Yeah. So this is plotting their messiness. So they had some certain threshold, and they said this is like our regular completion rate. So that's this dotted line at 0, 0, and then they're saying when we match that to the messiness, here's how much more success or less success we get versus the line that we expect. So the things that got a task messiness of 1, we had higher success rate. Lower or higher messiness, we ended up having lower success rate, which is what they would expect. But ultimately, with that one, they still saw that the better models are still better when the tasks are messy. It's just that the success rate is decreased. So one of the other tests that they looked at was SWE-bench. And so that's essentially looking at GitHub issues and then saying, can you complete the code changes that need to happen in order for some new tests to pass? So they say, make this thing have this new argument and make sure that it passes all of these tests, and then the system will go and try and make all the edits to the code in order to add that new feature, that new argument, whatever. And so they benchmarked a few of the different systems. So this is in addition to the previous ones. We're looking at those 3 sets I talked about, and this separate one was looking at SWE-bench, and they found roughly the same advancement rate. So they basically said, look, we've gone from these recent models and the tasks that took a minute. Now we can do 50% accuracy with GPT-4o. And we've gotten better, and we can do almost hour-long tasks with O1, for example. So the next thing that they did was try to extrapolate. So they say, we have this doubling rate. How long are we going to take in order to get to a month-long task that the AI can do? So right now, let's say we're at an hour. How many doubles do we have to go, and how long are those doubles going to take for us to get to a month-long task? So you type something into the model, and then it goes and works, and it can complete a month worth of work for you from that single thing. And so they're estimating based on various different things that we'll probably hit this around 2030. So they have kind of these uncertainty bars based on bootstrapping the different tasks. So they have their set of tasks, and they said, if I pull this point out, if I pull that point out, they just do sampling of it over and over again. And they say, what doubling rates do I get, and what's the range of potential future dates that we might hit? So they did the sampling based on the tasks. They did sampling based on the run. So they ran each of these multiple times. So they did it based on the models. So they say, what if we exclude Claude 3.7? What if we exclude O1? So they did samplings of the different models because one of the models might just be an outlier or something. And so this is kind of their baseline, just saying with what we have. And this is saying extrapolating from 2019 to 2025. They think it's maybe a little bit before 2030. But if they look just the improvement that we've gotten from 2024 to 2025, so you shorten up that window, then you say we've made so much progress in this 1 year. If we continue at that rate, we'll have a month-long completion in 2027, 2028, maybe. So these are crazy numbers. So it's assuming that we're going to just double every 7 months, which is, maybe we'll do that, maybe not, but it's kind of crazy to think that we would have a month-long task that can be completed by an AI half of the time. That's what this is saying. So the next section that they were looking at was the cost versus these systems. So they basically said, let's baseline at the cost of a Google engineer. So they cost however many dollars per hour. How much does it cost for them to complete a task versus how much does it cost for a model to complete the task? And so what they're showing here is that for many of these tasks, the model can actually do it at 10% of the cost or even less than the cost of a qualified engineer. So it's especially apparent in some of the shorter tasks where it's like, do you want your Google engineer to be finishing this line, or do you want the model to be doing that? The model can do it at such a small cost. You don't want your high paid engineers to be doing these tiny little baby tasks because it can be done completely trivially by the models. But we see that even for the longer and longer tasks. So the longer tasks cost more for the model, but it also costs much more for the person. So if it took 8 hours for a human to do, then it's going to cost you whatever the hourly rate is times 8, and then it's going to be the cost of the tokens or the agentic system or whatever against that. Um, so this is a big driver of like economic value. They're basically saying what is the cost of model versus the cost of human, and they're saying that there's like clear advantage to the AI systems for a lot of things now.
Do we know the particular properties that are allowing us to go through this period of doubling the time for finishing the task for 7 months?
I mean, they had some guesses about the next directions that we're going to go, but they're basically saying up to this point, we've gotten very far by just more data, bigger pre-training, some algorithmic improvements. And they said like that 2024 to 2025 boost, they're saying most of that is from the improvements in post-training and reasoning and test time compute and all of this stuff that like people have come up with just recently. They're saying like that's changed our inflection point slightly because now we can dump more compute at a problem and it can improve our accuracy at a lot of these tasks. Whereas before it was throw all of the effort into the pre-training phase. So they talk about various limitations to this. So they say we've scaled up to tens of thousands of GPUs. We're going to run into problems when we go to hundreds of thousands or millions of GPUs. Like we just can't produce that many GPUs. We don't have that much power. Like they talked about like these are strong assumptions that we're going to be able to keep just going up this curve. Um, they were saying that since 2019, the amount of compute that we've done in these models has gone up 10,000 times. So we can't go another 10,000 times in the next 6 years realistically, but we can have algorithmic improvements. We can improve our post training. We can put more effort at the compute after the model's already trained. So they're kind of saying like there's still levers for us to pull, but this is like a big assumption that we're going to be able to just 10,000x again. That's probably not the case. Yeah.
Okay. First question was, what is the model cost we're going to? Is it just the electrical cost? Is it the amortized training cost? Like what?
It's the cost based on the tokens of the model. So most of these systems, like if you go to Claude or something, they're charging you per word essentially. And so the cost of that is usually quite low. Like they've gotten it to the point where you can have 1 million tokens for $1.50, for example.
So its costs aren't factored in. But such as the initial point.
No, no, yeah,
So,
yeah. So it doesn't include training costs. No, it's just how much would it cost you to consume this and try this yourself? No, no.
Second question was, it seems like the 1 minute there's that trend. Is that just a feature of the? I guess what is that?
I think that it's because when we look back at this, yeah.
I think it's a fixed minimum model cost, and then the human cost just differs. So we do the ratio that if you have the human cost, but the model cost is just like at that minimum, then
I think that it's partially that, but I also think it's partially the gap between the data sets. So this software atomic actions, they have a bunch of tasks that are very, very short. And I think that that might be partially what we see here is like all of these tasks are the SWAA data sets, and those have their own certain property, and then the longer term ones have slightly different characteristics.
Right, so you mentioned it's addressing the token cost. Is there any metric saying, hey, a prompt engineer would take X dollars to actually write the prompt for sort of solve it in 1 second?
They didn't include that cost. So one of the things that they talked about was they had like completely minimal scaffolding, and they had an external team actually try to do some prompting, try to optimize, and they said that they only really optimized for Claude 3.5. So they went and they said, go have someone fiddle with this and try and get it to work with 3.5, and then they just broadcast that to all of the other models. So it's even possible that they're kind of underrepresenting O1 or some of the other models because they optimized for Claude first. But yeah, they didn't include that cost in my understanding.
For the delta between whatever the prompt engineer prices and the Google engineer price. So the whole thing should get shifted in some direction.
Yeah, yeah. So this is an interesting one because now they're just measuring the success of humans at these different tasks, and they're saying what level can a human actually complete these with 50% accuracy. So some of these are very long tasks. So they actually brought people in and they said, do this test. And some of the tasks are 2 days long. And so some of the people just quit or they couldn't complete it or they tried the thing and it didn't work. They didn't do it correctly. So they're measuring just humans and they're saying, how long can a human get 50% accuracy at these tasks? And so we have fairly flat performance and then past a certain length, um, they're saying we can do about 1 hour tasks with 50% accuracy. So one caveat to this is that they said the way that they motivated people is they gave people money for any problems that they got correct. And so there was motivation to go find all the easy ones and just complete them and then give up early on the ones that were particularly hard. So they were saying that there's kind of adverse pressure there. So you shouldn't really read too much into this, but it is interesting to see like what does our curve look like versus an LLM or an agentic system or something like that.
I wonder if the better method would be just spin those different length tasks and just have people come in and do those tasks. As opposed to like bringing a bunch of people, have them pick what tasks they want to do with.
Yeah.
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 It's a bit of a
I think it's there's plenty of tasks in there where it's like I could totally believe people just couldn't complete it regardless of time. So like that CUDA kernel one, I probably couldn't complete that in 8 hours or any amount of time. Like that might take me a week. Um, yeah,
like some of those could be like take homes.
yeah,
But then it would still be more of an advertising person.
yeah. Um, so one of the things that they highlighted too was they also measured the ability of, so the SWE bench is saying we're in some GitHub repository, we have some issue that's raised. How good is the model at actually like solving that problem and closing the issue? And then they were also benchmarking against the human. So they're saying, human, how good are you at taking this issue and actually closing it? And one of the things that they noticed was that a repository maintainer, so the person who wrote the original code or has been maintaining it and knows all about the repo, they're able to complete it well and much faster than a baseline person. So someone new walks into this repo for the first time, they don't have context, they don't know how all of the pieces fit together. They take much, much longer and they do a much worse job. And so one of the things that they were figuring out was if we do this based on the repository maintainer's time, then it really doesn't show the like apples to apples comparison because the LLM is going in there blind and just saying like, okay, for the first time, read this code, go come to some conclusion about how to solve this problem. And so they plotted it versus the repository maintainers, and the trend was like broken. And then they compared it against like a baseline saying, here's outside people looking at this repository for the first time. And then they said, okay, this trend actually holds again when we take external people and we say, go look at this. And one of the other things they did is they gave scores for one. A score of one was like the issue was correctly completed and it was just done. There was no further corrections. There's a 0.75 for if there was a minor nitpick, like you needed to add some doc string or change a variable name or something like that. And then a 0.25 was actually like some corrections needed to be made, but it was overall correct. And so they were finding that it's kind of interesting. A repository maintainer completes it in 20 minutes and gets it totally perfect, and a baseliner takes 2 hours and they still need some back and forth on this needs some correction. It's not quite right. That's just some external person, some software engineer looks at the repository for the first time and tries to close the issue. Yeah. And that's everything I have. Yeah, go ahead.
What is the score column?
That's the score that I was mentioning. So a score of 1 means like it was completely correctly solved. Score of 0.25 means that it needed some correction. So they needed to go back to the maintainer and say, is this right? And they said, go back and forth, fix this, fix that. Yeah. All right.
Okay. You know, I have kind of a really high level and sort of hand wavy question about this. And I'm curious, like, if the paper mentioned anything, if you have your own personal opinion about this. I'm kind of curious if if you believe that this time it takes a human to do something metric is a sustainable metric moving forward. Like, if like there is a point where, say, like an agent can complete a task that it would take a human like an unreasonable amount of time to complete, like a month, which is something that I don't think anyone's going to sit down and work on like one thing for a month. So it might be outside of the scope. Like, will that continue to be a meaningful metric, or do you think that there will be like a cutoff point? What does it mention?
I think it breaks down past a certain point, but I think that's like at that point you say, okay, we can complete a 1 month task 50% of the time. I think that's already like such a high bar that that's essentially saying, okay, I have like this thing that's like set up a whole website or company or something like that. And then you just say, throw out 5 prompts and see if any of them hit. And then you have a whole e-commerce business that's just popped out of. So I think that's my personal bet is that we're not going to get that by 2030, but maybe I'm misguided. But I do think it breaks down.
I think you're thinking of like how would you do a study about this or something like that. I think it's just a very expensive study. So then you have to pay someone 1 month of labor for however much that person's labor for a month. Right, like you said, start a business in a month. Right?
It's kind of like how they measure like chess balls. Like the ELO rating is by like, say, relatively other players, but there's no players that are rated 3,100 or 3,800. So I think after a certain point it would just be kind of like, okay, this is like roughly speaking what we would imagine would be in context or something.
So extrapolate from a lower version.
What you could do for a data set is look at open source projects that have regular updates, estimate how many hours were spent on that based on check-in, check-out points. We have those metrics and then say, hey, get your AI do this, how many prompts do you do that kind of thing.
Yeah.
And even if you're right that it breaks down, I love that we're talking about a numeric metric, because all these other conversations around intelligence and ability have been just not numeric. They've just been very qualitative.
Big task, it's not going to scale linearly.
I was wondering about that too, right? Because like, it looks like they're doing, like, how are they getting that projection? I'm reading the next paragraph and like, they talk a lot about how they get these different categories. I'm looking at figure 12 in the paper. And, that's what the slide I got on. But, they have this, oh, by 2030, we're going to get this result. And is that a simple linear chart? I actually, maybe it says it's simple, but I don't see it.
I think they're just talking about cumulative time, so if you double every 7 months, then you'll get to a 30.
Yeah.
Yeah.
It's more slow and everything else, still, no, that's where it would be.
Yeah.
Ryan mentioned that they're not saying that it's gonna continue to go, because you're not gonna have
But
10,000
that's what we're
times
getting.
the number of NVIDIA cards
Yeah.
in 3 years.
Correct. It's not a prediction, they're just simply saying that's perfect.
It's the current tangent.
Thanks, Ryan.
And question, what was the source of that last table with the essentially repo maintainer versus baseline?
That was in the appendix of the paper. So they have more details in there about that.
Literally the program.
You want me to mute and you do the audio, or?
All right. Um, I really love that paper. Thank you so much, Ryan, for sharing that. I think this one may not be quite as thought-provoking, a little more fun paper. So this is a recent model from NVIDIA called Describe Anything. And I'll talk about what the problem is. This is not exactly a use case that I was super familiar with, but I think it's a very cool problem. So the idea they have is they want detailed, localized captioning. All right. So if I give you an image, and let's say it's a scene from a cooking show, and you see somebody cooking there, and they've got pans, and they've got bowls, and they've got cutting boards, and all this stuff or whatever, right? We've got models that are pretty good at just captioning and describing what's going on, and you could ask for more details, okay? But what if you just wanted to know about this one something that's like sitting on the cutting board, okay? Or you had a picture of a skyline and you just wanted to know about one building, not the whole thing, okay? And I guess, you know, the two approaches that people have taken is you can use a bounding box or you can use text to try to describe what your object of interest is. So like describe the green thing that's on the cutting board, right? Describe the building that's kind of farthest to the right in this shot or something like that. And there's flaws right there with just right trying to localize it or whatever. But then even if the model's able to figure out exactly what you're talking about, there's this problem that if you give it the whole image, it tends to think about the whole image, right? So the embedding is based on the whole image. And so how much detail it can give you about that one little thing tends to be very limited. So you get these vague descriptions, okay? And so to make up for that, another approach that people have done is they say, I'm going to crop around that object and give that to the model. And now it's like, oh, now I see this. This is the building that you wanted me to talk about. So I can talk about the architectural style and, you know, the kind of windows and da 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 da. You know what? It can go into a whole lot of detail. But the problem is, especially when you have small objects, right? It's like, oh, I cropped this tiny little thing, and now the model doesn't even know what the heck it is. It's like, what is this? Is this somebody's Legos? Is this some gray fuzzy thing? You know, it doesn't even know that it's a building anymore if it's like a small crop. Okay. So the idea is like, is there a way we can have the best of both worlds? And apparently so far, this has not been a well-solved problem. Okay. So, you know, like the latest, you know, GPT, you know, 4.0, whatever, it does like a decent job, but it's still not like really bang up. Okay. So those are the two trade-offs from the obvious solutions of give it, the whole image and it has all the context it needs, or give it a crop and um, uh, then it can really zoom in, but it doesn't have all the context. So ultimately, what they did is they built a novel input backbone, um, and they then fed that information into a pre-trained LLM. So there's sort of these two parts. There's sort of like the vision backbone, and then there's the LLM, which is not particularly, it's fine-tuned, but it's not particularly changed from its initial multimodal training. All right. So here's just a diagram from the paper. I think I kind of already covered this, but so you can imagine that like here's this very busy scene, and they wanted to know just about this little green thing, which is a relatively small object out of this frame, right? And so if you take some of the previous papers and you give it this, um, then you tend to get a fairly limited description of this like dark green circular object or whatever. And if you zoom in on it, then it's like, oh, I can tell that this is actually a mouse or whatever. But maybe it's wrong. Maybe that's not a mouse because now it actually lost completely the context of this is a kitchen. This isn't somebody's work desk, so it's not actually a mouse. It's something else. All right. And so a couple examples, they built this so it could work on still images or it can actually do video. Video meaning like, 8, 16, 30 frames, right? We're not talking about like true video, whatever. But so you can see here, we've got a picture and we've got a bunch of dogs in the snow. I don't know if this is like a dog sled thing or whatever, but they didn't ask about the big dogs here. They asked about this dog that's a little bit smaller and off to the left. And then they're able to ask for a detailed description. And so then it can really go and say a white, fluffy dog, thick coat, pointed ears. The dog has a wide open mouth, pink tongue is hanging out. The eyes are dark and alert. Like there is like way more detail than you would ever expect to get from a model that you gave just the whole image. At best, it's going to say, something about it's a white dog, it's whatever, right? And then here's an example from the video. There's another example that I didn't include in my slides, but it's a car, and you see it from different angles. And so, like, one of the things in the description is that it's one of those cars that has like the spare tire on the back, but that spare tire on the back's only visible in one of the 8 frames. It's not in like the other frames or whatever. And it like well integrates that. Oh, here's details about the front of the car. Here's details about the back of the car. And it does a really nice job of integrating those. So how did they do all this, right? Before I get into that, I just want to say there's I think 2 big takeaways from this paper. And one of them relates to the specific solution they came up with. But the sort of meta thing is that what we've seen in a lot of deep learning problems where someone's trying to take on a new problem, someone's trying to make large progress in a domain where very little progress has been made to date, they're going to have 3 problems. They're going to need some kind of good architecture. They're going to need training data because they just won't have that much of it. Okay. And they're going to need a way to accurately measure performance. So when you're in an area where there hasn't been much progress, you usually don't have any of these 3 things. So we saw this with, I'm just trying to think like, at some point, we saw it with reasoning models. We saw it with like alpha geometry, right? There's just not that many example math proofs for you to say, deep learning models are usually really, really smart, but you need like typically million or billion scale examples of training data to get these deep learning models to learn. Yes, sir.
If at all, by the idea or concept of memrisers.
Of what?
Memrisers.
I'm not familiar with that. I can't comment on that. So, yeah.
What do you mean by architecture?
So I'm saying like AlphaFold, there was a particular model where they had these transformers and this that, and they represented the data this way. So you do need to do that, and so right, oftentimes, for me at least, like that's kind of the first place I go to. It's like, oh, here's a new LLM. Oh, look, it has mixture of experts. That's a new architectural change. Oh, look, this one has blah de blah, you know. But much of the time, when you have a domain that's not as thoroughly studied, the problem you have is just the lack of training data, you know. So, oh, I have lots of images off the internet, and I can build a wonderful image classifier or segmentation model. Now I want to do satellite imagery. Sort of image segmentation is a solved problem, but I can't actually give you a good satellite segmentation model because I just don't have enough training data that's labeled so that this is what from a satellite at whatever 30,000 feet, you know, what a barn looks like, what a car looks like, what an 18-wheeler looks like, right? You know it's solvable, but you just don't have the data.
Kind of like state.
Yeah. So, so, so I think this is another takeaway from this paper that, you know, I'm going to talk about the architecture. I really like what they did there, but understand that really it's pretty common that you have this issue where maybe all you need is a tweak like mixture of experts to get your LLM to be a little bit better. Maybe what you need is actually more data, better data, cleaner data, something like that, right? Um, so in this case, we'll get into what the architecture is. Um, but for the training data, one of the things they had is that the benchmarks that are already out there, most of the captions were not these detailed captions. You know, so it's like in this one, it's like a white dog. Well, how do I train my model to give detailed things that say the tongue sticking out and the ears are this way and da if I don't even have any training data? The training data all says a white dog, right? The problem they had is that historically we had bounding boxes, and so they gave an example of here's this dish being served, and you put a bounding box around it, and like, do you want the model to describe the plate, or do you want the model to describe the food that's on the plate, or both? Okay, it's ambiguous when you just have a rectangle around something. In many cases, it's not ambiguous. Like if you had the dog there, I think it would be pretty clear. Like they're not asking you to describe the snow that's behind the dog, you know. But there are lots of situations where there's this level of ambiguity. That's the problem is they can't. So ultimately, what they did is they went to segmentation max instead of bounding boxes, and so they said that's how we solve this problem. Um, and then in terms of performance, one of the big issues they had was uh, if the reference caption says a white dog running in the snow, okay, and you said a white dog with a pink tongue sticking out, and it's got this kind of ears and it's got that and that, and those are all accurate, but they're not in the reference caption. Most of these other benchmarks would penalize you because it would treat those as if they were incorrect. It would treat them as if they were hallucinations. So so when your reference isn't somehow all encompassing and perfect, then you can't tell whether a fact that you included was leakage from the rest, right? So I guess in this example, if it was pulling a dog sled, they didn't want any information about the dog sled. They just wanted information about the dog. And so if you said pulling a blue sled, you should properly be penalized for that. But if you said with a pink tongue hanging out, that's actually right, and you shouldn't be penalized for that. So how do you solve that measurement problem? And so then they actually built their own new benchmark to solve this problem. And then also they commented that for scaling things, a lot of people are using LLM as a judge. But again, vanilla, there wasn't an easy way to use LLM as a judge. Hey, Ryan, are you following the chat? I am not currently monitoring. So if there are comments, fine, but if there's question, I don't want to ignore it. Yeah.
So like with the dog, yes, it is off to the left, it is pulling the sled, but it also has some sticking out and snow, it's walking on snow. Is it trying to get everything under the sun to describe that or what?
Yeah, so the question is like what do you want? Do you want everything under the sun in the description? Uh I don't know, like I'm not actually the researcher, right, on this paper. What I'll say though is that they basically had no data that was more than a 6 words long-ish, right? So they just had like zero data that was 3 sentences, 5 sentences long. And so they really, really were data poor on this particular problem. All right. So to preview what we're going to talk about in the next few slides, and I'm not going to go into super detail on all of these things. I've got like, I don't know, half a dozen more slides, whatever. But so for the architecture, what they did is they didn't use bounding boxes. They use segmentation masks. And they said, why choose full image or crop? Let's use both. So their input is actually 4 items now. It's full image and the tiny segmentation mask in that full image for the object you care about, and a nice zoomed in crop of what you care about, and the segmentation mask. And so in the case of like the dish, if you wanted the food to be described, your segmentation mask would be this rough thing that's inside of the circle. If you wanted to describe the plate it was on, it would be just the outside of the circle where you see the white of the plate showing through. And if you wanted both, then your segmentation mask would actually cover the full circle and everything in it. And um, that's the concept of how the segmentation mask is more accurate and more detailed than a bounding box would be.
The whole image contextualize the other 2 layers, segmented box.
Yeah, so we haven't talked about how they're going to do it, but the idea is we're not choosing between zooming in and the full image. And so in the case where there was like this small building and it wasn't even sure it was a building anymore, now you hopefully have the context where you can clearly see it's a city skyscape, and then that's hopefully enough grounding that you don't accidentally think it's Legos or it's a gray carpet or it's a whatever, right? Because you have objects that are occluded, so their shape is not necessarily right. So there could be like a building and there's a tree branch in the foreground that blocks it, so it's not fully a building shape anymore. It's got this part cut out of it. So for situations like that, that's especially when I was playing around with it, I was trying to see if I could trick it, and I did get it to fail on certain circumstances where it was like uh, if we have time, we can play with it. But so there was like this circuit board, and it had some multi I don't know what you call it, multi connectors, right? And when I found one that was occluded, you could only see a little part of it. It thought it was a Lego, thought it was a green Lego, but it was actually like. But when you have the whole thing, the hope is that you see it's a circuit board, and so you're not going to assume it's a Lego. You're going to assume that it's some kind of connector on the circuit board. Did you still have a question?
Yeah, how does it relate at all to digital engineering? Where does like electrical engineering, systems engineering, mechanical engineering, how do they fit into this new? It seems to me to be a new CAD pipeline that's better.
Yeah.
Straight clear on one-dimensional architecture.
Yeah, I can't comment on how this would. I don't know that much about electrical engineering, but clearly, if you're using LLMs for a lot of things, then we would like to not just have global descriptions, but we would like to be able to have them drill into parts and subparts and be able to be more fine-grained about that. So I think this is very visual right now, but I think you can also imagine how this might apply in modalities other than just image. Yeah.
Assuming that most of what we're talking about here is just talking about conventional computing architecture, CPUs, graphics cards, neural processing units, that kind of a thing. We're not. You're talking about memory.
Yeah, so different trajectory and NVIDIA should be going right about now.
Yeah.
Yeah. So I mean, this is machine learning. So this right. Ultimately, the model is agnostic, but yes, this is NVIDIA. So guess what they ran this on? They ran this on A100s. Okay, because these are people at NVIDIA. Okay. So then the second problem is the data problem, and they had a semi-supervised process that they used. They had to create their own training data, right? We've seen this many times, and this one's a little bit different than some other ones, so we'll do a slide on that and talk about that. But they had to solve that problem. And then their benchmark, we'll go into the details, but basically what they had was they had specific questions for each of their benchmark samples where they had positive points and they had negative points. And they only rated you on the positive and the negative points that had been pre-developed. Okay. So for example, the dog with the pink tongue sticking out or whatever, they might have something that says, I'm going to do negative points if you talk about the sled. I'm going to do negative points if you talk about a different dog. I'm going to do negative points if you talk about the sky. You won't get penalized for mentioning the pink tongue if that's not part of their reference example, because basically we're not sure if the pink tongue is an accurate detail that we just didn't include in the reference or if it's a hallucination. So what they tried to do was to come up with the likely mistakes that a model would make, the extraneous things that it would include. Okay, so it's not necessarily perfect because they're not going to cover every possible hallucination, but this addresses the issue of how can you possibly come up with every positive thing that it could possibly say? Because maybe one model talks about the ears, the other one talks about the eyes, the other one talks about, the paws, something talks about breeds. Who knows, right? And those could all be accurate. You just didn't know, as the person who was creating the caption for this image, that there's this history about this breed, that it came from Lithuania. Like, it could be completely accurate. You just don't know. So they only penalize it for their predicted known negatives. That's what we're going to see.
Yeah. So actually, on it, your combined full image frame and props.
Yes.
So I do a little cartoon on my note sheet. So you have the whole image, right? That's the frame, and then use that for context. But it looks like there's also, I'm imagining also like there's a bounding box around that. Within that bounding box, you have a segment.
Yeah, I think it's the next slide. So it's
Okay.
probably the perfect segue. I don't remember if I have another slide in between or not. Yes. Okay. So so how the model there's two slides together here. So how the model defines its inputs. Okay, it says we're not going to use bounding boxes. We're going to use segmentation mask. Okay, and we're going to have a pair of an image and a segmentation mask. And in this case, we're going to use two. We're going to use the full image, and we're going to do a crop around the object of interest. Okay. Ultimately, what they used in their model was 3 times. So if the image is yay high, they would go that much above and that much below. Okay. And if it's so wide, it would go that much to the left and that much to the right. Is that exactly the right choice? Hard to say, but that's what they did in this paper. Yeah. Yeah, so great question. So did they train on all the different possible segmentation masks? I'm pretty sure the answer is very much no. It's that on different images, there's different segmentation masks, and you hope that you get enough diversity that ultimately it will work. Hypothetically, you could have said on this one image, I'm going to have like 150 different training examples based on the different possible segmentation masks. And it seems like that really wasn't their strategy. It's like, on this one, I'm going to have one segmentation mask. And then hopefully later on, I'll have a very similar image and I'll have a different mask and we'll get enough coverage that way. That's what I got from the paper. I might not have gotten like every detail in terms of how they did it. Okay. So not going to talk about video too much, but ultimately video was just a sequence of frames. So like, you can imagine 8 frames. Otherwise, it works largely the same way as a single image. Yeah.
So on point 3, looks like it is, so it takes the full image, it takes crop, but it also takes full image, it takes the segment mask. And then it also looks like based on the point, it takes a crop. What is it doing with that crop that it wouldn't be able to do with the entire image? Like, is there additional context in that crop?
No. So what we're going to see is that largely models do better with the crop than they do with the full image. So they're going to say, start with the crop, but I'm also going to give you as context the full image. So I would guess, this is a very loose statement, okay? But I would guess that 90% of the model's energy is looking at the crop, and 10% is just, do I have the right idea of what this is, right? So if you had a dish and it was relatively small, might not be high resolution, like you might not even know it's food. But if you give it the full image and it's like two people sitting at a dining table and here's a white round plate that this crop lives inside of, then hopefully you're like, okay, I might have to do a little bit of guessing here and inferring, but I'm gonna do that along the lines of this is food, and then maybe I'll say this looks like an eggplant dish or something like that. But without that context, you might be like, ugh, some purple and some brown. I don't know what this is. So
It sounds like the regional, most of the cerebral power is just focused on that one point, but
yeah,
then you use your peripheral vision in order to contextualize
yeah,
that one.
yeah,
Right? Like, something up on the big picture thing with the LLM itself, that's gonna arrive naturally. The solution already provides and trained on them. So if you're gonna get Dijkstra's, you're gonna get Dijkstra's from it. That's frequently what you necessarily want when you prompt it.
yeah. So I'm not super well read on this, but I think what other people have tried to do is to architect to get like the attention layers to focus on the object of interest. And they just said, why don't we just do this in a much more explicit way by passing in the full image in a separate path from the crop? And so instead of having it really like try to get it to focus, it's like, no, there's literally two separate paths, one for general context and one for exactly what it is you're supposed to be describing. Okay. Um, yeah, so I think I covered this. So let's go on to the next slide. And so this is the details of the architecture. I'm going to spend a little bit of time on here. Okay. So everything in the dotted box on the right is what they call their localized vision backbone. Okay. And there's these two other papers. There's this SIG-LIP paper where they basically had a VIT and they trained it. Not going to go into the details that, but they had some contrastive loss for jointly training images and text. So basically, think of this as a clip, right? This is a clip-like model where you're matching up text and images. Okay, and so then on the next slide I'll mention, and so then there's another paper that is this multimodal LLM. So it already knows how to do text and it knows how to do images, and you could just take that model and you could ask it to do this problem of, hey, give me a caption for this one particular dog that's part of this overall image, and it would do this, and that's, you could argue, like a baseline competitor for this paper. Okay, so the LLM at the top, I apologize if it's partly obscured by my Zoom windows. So this is a pre-trained LLM that already could do this task at some core baseline, level of capability. So most of the innovation is what's in this dotted box. That's why we'll take a minute and talk about this dotted box. Okay. So what we're going to do is we're going to take, let's just start on the right bottom here. Okay. This is the crop. Okay. This is the zoomed in portion of the, oh, actually, sorry, one more thing. Uh, in order to make life easier on people, because segmentation masks are a little bit of a pain in the neck to like sit there and like click every pixel or whatever, they said, segment anything exists. And so segment anything, you can just do one point on the dog and just basically it'll say that, or you can kind of scribble a certain number of points, or you can draw a box, you can do different things. And so basically they said, in order to get the segmentation mask, we don't have to reinvent the wheel. We can just basically use segment anything or SAM2 to allow you to very quickly and easily generate segmentation masks. And generally speaking, you know, I've looked at SAM. It does a good job. If you really wanted just the dog's head, you know, you can put a dot on the head. If you want the entire dog, you can either put a dot on the head and a dot on the body, and that's enough of a contextual clue that it'll do the whole dog, including the tail and the legs. Or you can draw an approximate box around it or whatever. It is pretty smart and pretty easy to get like the segmentation mask you want.
Like draw your mouse around it so you could draw.
Yeah, and you don't even have to really draw it. You can literally just do a couple clicks, you know. I believe so. The demo website doesn't have that, but I think ultimately they did. But the point of this isn't really even about that. It's really about that this is existing technology, so the paper's not going to focus on that part of it, right? The how you get the segmentation mask, they say, is kind of a solved problem. So we're not going to talk about that. The other thing they say is that if you have a video, it's a similar thing. You could use SAM2 or you could use some other model. You can use optical flow. If you just get a segmentation mask of a car in one frame, there are other models that will then extend that to the frames before and after. And so you can have accurate segmentation masks across multiple frames, even though the camera might be moving, the car might be moving, your perspective might change. All of those things, there's already existing models. So they say basically this paper is not about those technologies. Those are pretty much a solved problem. Yeah. Yep. Yeah. Yeah. So this paper is really about the captioning. So I just wanted to mention. So they say like, hey, we're not going to focus on these parts. Which parts are actually like in their demo and which parts are not? I don't know, but that's not really the point of this paper. Okay. So we're just going to talk about images. Basically, for video, just imagine you did this like 8 times or however many times, you know, one for each frame, and you concatenate them. Okay. So in the lower right, we have the zoomed in portion, and this is where I'm saying this is the core of what the model is doing. Okay. So basically, we're combining the image and the segmentation mask. I ran out of time to actually look at the code. I'm not sure actually if this is concatenation, but I think it's concatenation. Okay. Um, um, but anyway, so then this goes into this SIGLIP VIT style model. Okay, so this is just this regular vision transformer, and if you go into that paper, you know they did some tests on whatever VIT large, VIT medium. You know, I'm not exactly sure the details, but again, that's not really the point of this paper. On the left here is where you see they have the full image that they also did, and this segmentation mask is basically the same as this one. It's just not zoomed in. So, right, you can't really see the details, but it's the exact same shape as the one on the right. And they send this into, again, this uh, BIT-based image encoder in order to save memory and speed things up. These two vision encoders share weights. So ultimately, when they fine-tune this model, the vision encoding is the same on the full image and on the crop. And that kind of makes sense to me because people do a lot of multi-resolution training in computer vision now. And so the same feature extractors that work on the crop, generally speaking, should work on the full image. The thing that is different, though, is that on the path for the crop, they have this extra cross-attention layer. This is where the global information from the full-size image gets blended in with the crop information. Okay. And so if you remember, like the original attention is all you need paper, right? In the decoder, we had self-attention and we had a cross-attention from the encoder. So you could say that this architecture is now reminiscent of that, where you have the encoder on the left And then over here in our decoder, we have self-attention, and then we have our cross-attention layer. I don't think that's a great mental model, though, because the purpose of these two left and right halves is not really the same. In that paper, it was like English and French, it was language translation. So I wouldn't go too far with it. But if you're just wanting architecturally, this is the same complexity as the decoder in the original. I don't know if I can comment on that statement. But so the idea here is we are slightly modifying VIT in order to bring in this global context. Okay. The really interesting thing that they did, I don't know that this is novel, maybe this has been done in other papers, but if you look at these two pink boxes that have the segmentation masks and this orange box that has the cross attention, they applied a scalar gating mechanism to it, where the outputs from those components would just get multiplied by this constant. Okay. And this constant can change during training. But what they did is they set it to 0 at the beginning of training. So they basically completely wiped out the segmentation masks. Okay. And the gated cross attention was completely wiped out at the beginning. So the entire portion of the full-size image got zeroed out at the very beginning of training. So if you look at that, if you zero out the orange and you zero out all the pink, what's the only thing that flows through is your cropped image. Okay? So if you think about it, if we wiped everything else out, now this is the pre-trained SIGLIP model with no modifications whatsoever, because everything else is zeroed out, and all it's doing is embedding an image like it was pre-trained to do. So the output of this model at the very beginning is identical to the pre-trained model. There is no domain shift whatsoever for what this is being asked to do. Gradually, as you let the constant on the masks go up, now you're not just looking at an image, you're looking at an image and another channel or an image and whatever, so that it can then say, you basically want me to sort of ignore the masked out areas and really just focus on this, I don't know what you would call it, vertical, oblong shape, right?
Don't they focus only on the focal prop?
The pre-training was just a regular image encoder, so it took rectangular images and looked at the whole thing. It didn't know about segmentation masks.
Okay.
So this is the idea, to introduce segmentation masks gradually,
Okay.
so that you can use the pre-train. They could have trained this from scratch, and then they would have needed what, 50 million images, right? But if they train it using the pre-trained thing in a way that doesn't cause any catastrophic forgetting, doesn't cause any domain shift, massive domain shift, then they can say, I only need 1.5 million examples, and I can take it from a vanilla image encoder to one that understands images with masks. And then I can take it from images with masks to images with masks combined with global context images. And that's the part that one of the things I really like. Again, I'm not sure, maybe other papers have done this, and so they would say, I can't take any credit for it. But this probably reduced the amount of data they needed to train this by 2 orders of magnitude. Okay. The fact that it starts out doing exactly what it knows how to do, which is just encode an image. And then gradually, as those 2 separate parameters move up from 0, now it's including more of this information. And when it includes more of the information, it will be able to do the task better. So the gradient signal will point towards like increasing those and giving it that information. But it'll happen very gradually, assuming your learning rate is small. And so the idea is that we don't cause any kind of sudden domain shift, and we gradually get more and more of the segmentation info, more and more of the global info through this cross attention. And then voila, by the time it's fully trained, it now knows how to use these 4 inputs on a model that was trained on only 1 input. So I really like that. I thought that was kind of clever. What happens after you embed this is the vanilla process from this multimodal LLM. Okay, it's actually not shown in this diagram, but there's a two-layer MLP that projects the output from the VIT into token space for this LLM. Okay, so this LLM is already pre-trained to do multimodal, but it's not pre-trained on this particular kind of segmentation mask, kind of a multimodal thing. So they do a little bit of joint fine tuning of this whole system of the LLM and the backbone. So in terms of that training, you can see here's this Vila model. This was a bunch of other NVIDIA people. Okay. And so there's models that are out there. You can get them from Hugging Face. So when they did their experiment on just images, they used the smaller one. They used a 3 billion multimodal LLM. That's pretty small, you know. For videos, it has to take like these 8 images concatenated, and so they use a slightly bigger 8 billion version of the model. The way that this vision backbone works, the way that they gradually got it to understand how to do 4 inputs or whatever, what ends up happening is its output is the exact same dimensionality as the original pre-trained VIT. And so the context length, the sequence length for the LLM is no greater than it was in the original Vila model. Okay, so one thing you could have done is a very simple thing you could do is you could say, no, I don't need to do any of this fancy vision stuff. I'm going to pass all 4 things, the big image, the big segmentation mask, the little image, the little segmentation mask. I'm going to pass them just through a vanilla encoder, and I'm going to concatenate all 4 of those and pass them into the LLM. And then what you're doing is you're quadrupling your sequence length for the LLM. Okay, so by doing this, they did not grow the sequence length of the LLM, and they also minimized sort of how much domain shift there is for the LLM, because it's still getting exactly the same number of tokens per image, the same, general concept. It's just that hopefully the vision encoder is going to encode much more of the specific details about the segmented area and less information, if not none, about the non-segmented area. Yeah, so they did some end-to-end training for this whole thing. And one of the things they did was while training, there may have been more details, but I didn't bother. They alternated, they mixed in text-only training because they didn't want the LLM to sort of forget, have any catastrophic forgetting of its regular text training. Okay, so that was part of their recipe. I'm sure they tried not doing that, and they found that it degraded its language performance. So they said, okay, we're going to mix in this captioning training with just regular text training. And at the end of the day, 3 billion model is not, it's not huge by today's standards, right? But it's not small, and they were able to train this 3 billion model on 8 A100 GPUs. So I'm assuming these are 80 gig RAM GPUs in under a day. They didn't even specify exactly how long, but it was like 1 day, right? So like, not that I would want to, but hypothetically, if I had the data set, I could reproduce their training. That wouldn't cost, I don't know what that would cost. Like, yeah, a few $100, right? Like, so this is, quite reasonable. And again, a lot of the choices where they said we're going to take pre-trained models and we're going to minimize domain shift, we're just going to cause it to fine-tune in the direction of understanding this specific task. That's what I think really minimized the amount of data and the amount of training that they needed. So that's one of the things that I think is pretty clever about this. Yes, sir. They could be doing distillation. In this case, I think that it's only 1 day, so this is actually already a very efficient training process. Taking advantage of the vision model was pre-trained, the LLM was pre-trained, right? And so can we take advantage of the fact that they're both pre-trained and just try and do a little bit of tweaks to each of them to get this to work really well for our task. And by and large, it seems like it really did. Minor detail, they wanted the ability to have tunable prompts so that you could ask it for a short, more traditional caption, or you could ask it for a longer caption. And so what they did is they said, in some of our prompts, 20% of the time, we're going to append in 1 sentence, in 3 sentences, in 5 sentences. And so the in 5 sentences is going to pressure it to write these really long, detailed captions. They also 20% of the time did words. Okay, so if they had something, they could say in just 3 words. They say in about 50 words. And for the really long ones, they would say in more than 200 words. Okay, so in the end, they show examples where if you don't want the white dog, the pink tongue, here are the ears, here are the, if you just wanted to know it's a white dog, you could actually ask it to give it to you, give me a caption in 5 words or less. And the LLM knows how to do that. Okay, so that's the vision thing. One slide here on the data pipeline. They basically had no data with long captions. So the first thing they did is they found some segmentation data sets, and these usually had a class name or some other short thing. And so here's this data set, which was meant for training image segmentation models, right? But it says that like this segment, it's a tomato, it's a car, right? It's a tree or whatever, right? So they have that hint. And what they found was if they gave the image and that super short description from the segmentation data set to the Vision LLM and said, give me a longer description, the Vision LLM was actually pretty good. They're like, oh, I know that you want me to talk about the tree. I'll give you some more details about what color the tree is. Is it bright sunshine? Is it whatever, how many leaves, whatever. So the first step was they just took existing segmentation data sets and they asked an LLM to expand the length of those. So they weren't able to get the LLM to just write a long caption from an image, but given an image and a short description, they were able to then get it to write a long description. So they did a certain amount of this, and then they had a very early, describe anything 0.1 model. Okay. They then took that model and they iterated. What they did is they said, let me just scrape the internet and pull down images, and I'm going to run existing open vocabulary segmentation models. And the segmentation model says, I found a tree in this image over here. They're like, great. Now that I have this 0.1 that kind of works a little bit, I'm going to have it write a long description. Okay. And they needed some kind of filtering because sometimes it's going to write good descriptions, sometimes it's going to write terrible descriptions. So their technique was they used clip to say, does this tentative just long caption match the image? And they kept the highest. The intent was the highest quality ones by using that signal. And so then you just keep iterating this. And so this is where the semi-supervised process comes in. And then hopefully it gets a little bit better after that iteration, right? And so then you scrape some more images off the internet and it writes even better descriptions. And then you train the next version on those better descriptions. And then you iterate, and the next thing you know, you have 1.5 million novel triplets of an internet image you scraped off the internet, a segment mask that off-the-shelf model gave you, and a beautiful long description. Okay. So this is the way they bootstrapped from having absolutely no data to having 1.5 million training examples for their model. All right, and then the last thing is benchmark. Not going to go into too much detail on this, but they wanted. I don't think this benchmark is perfect, but I do like what they did. I think it's better than what was already there. So they wanted to get rid of the need for comprehensive reference captions because basically they argued it's impossible for them ever to be comprehensive enough. Okay, to be fully comprehensive. So as I mentioned briefly, they curated positive and negative questions about the region, and then to scale it, they used LLM as a judge. Okay, if you go into the paper, the details are sort of like for a positive question, they would say like, here's like the control panel for a stove in the kitchen or whatever, and there'd be details about the knobs or whatever. And so you get a point if you mention that it has black knobs, and you get a point if it mentions the knobs are round, it gets whatever. And then on the negative side, it's like it was an electric stove, and so they're like, oh, you lose a point if you hallucinate that it's an induction stove. You lose a point if you say it's a gas stove. You lose a point if you mention the whatever the sink that's next to the stove, whatever, you know. And so in my mind, clearly these are not perfect, but they had to design a way where if you gave a detail that was accurate, but it just wasn't in the reference, that you don't get penalized. So if the model's somehow smart enough to say, oh, I actually recognize that stove was made by LG. We don't know if that was right or if it's wrong. You don't want to penalize it for things that might be right. So they just tried to come up with. So this is very handcrafted. I don't know if this is perfect, but it does seem like they address the issue that if you do some type of word, phrase, bigram match kind of a thing, right? Then you're basically penalizing it for anything it says that wasn't in your reference. And how do you ever know that your reference is perfect enough for all the details that, you know, would be valid descriptions? The other thing is using LLM as a judge, it doesn't have to word it in the same way as you. So like, you know, that's a problem with like rouge and blue and all this, right? Where you're using exact word matches. So when you use LLM as a judge, if the reference text says, you know, they should describe the knobs on the stove as being round. If the LLM says circular or oval or whatever, like the LLM as a judge is probably going to say, yes, that's a match, and give the LLM the point. So I don't believe, I may not have read it close enough. I don't believe the assigning of points is actually done by the LLM. The LLM just says like, how does it rate on this sentence? Is this a match or not? And then externally you say, for this match, you get a +1 point. For that match, you get a -1 point. And so that's the idea of the benchmark. And then here's an example. You can see the stove. They drew a pink box around it, but it would actually be a segmentation max in the real a pink outline. It would be a segmentation mask. And so here they have there's more than one set of questions, okay? But this is just one positive question. It says, which of the following is applicable to the description? And then, you know, the control panel is not mentioned. The location of the control panel is mentioned, but is not the back. The location of the control panel is mentioned and is in the back. And so C is like the answer that's going to get you a point, right? And some of these are going to be 0 points and some of these are going to be -1 points. And so the LLM is going to judge like which of these handcrafted descriptions is most applicable to whatever the description from the LLM was. And then basically you do the + points and you can see. All right, so we're over time. So briefly, results, it did really well. You can see there's actually some very large gaps. In some cases, it's like it did 1/3 better than the best model of the previously best model. So if the previous best model was like, you know, whatever, a 60, then, you know, they got 80, right? 1/3 better. So this is not like, you know, one of those things where you say it's a couple points of improvement. It's like a pretty large gap. And I don't know these benchmarks, but they talked about some of them are shorter, like keyword level, and some of them are longer phrase, more detailed. They have their the benchmark that they did on the right. And so this benchmark they think is a little bit more accurate. And so you can see some of the details here, some of these other models, how well they did. And then they had some video data. Here's like one example here of its performance on video benchmarks. So to wrap things up, they did super well on these benchmarks. Of course, every paper, right, you publish the benchmarks that you do well on. So that's not really surprising. But I do think this is an interesting paper because, again, they showed this typical problem where you have your model design, you have your data, and you have your measurement. And often have more than one of these that you actually have to solve in order to address a problem. And I like the fact that they figured out how to maximally leverage the pre-trained models that they base this on. They didn't just say, here's a good VIT architecture that I'm going to use as an encoder. Here's a good architecture and use an LM. No, they used the pre-trained weights and required minimal changes to those pre-trained weights, which was really nice. And they have a project page, and so you can do a demo with the images. You can see the GitHub repo. I saw there was a link for video, but I didn't necessarily quite understand. I think maybe you have to uh, uh, stand up your own grad.io demo, but you can. They showed here's the code you'd use to grab the video model, and then you could actually upload your own video, and you can play with this model. And then in the slides that I'll post, the reference, this is just the previous multimodal LLM. That's an NVIDIA model, and then this SIGLIP paper is not it's not an NVIDIA paper, but it's the one that was used in Vila and then carried over from Vila to describe anything. All right, I got it. All right, thanks everyone. We started a little late. We went over time, but tried to keep it closer. So we'll officially wrap things here.